So, welcome to this lecture on cryogenic hydrogen technology. We were talking about the hydrogen production, and there we have already learned about the different processes of getting the hydrogen. You may remember that we were in the last lecture we have talked about the hydrogen production from the coke oven gas, and there we have talked about the source of what is the source of this coke oven gas and what could be the possible composition, the typical composition of the coke oven gas, and how we could possibly get hydrogen from the coke oven gas. So, you may remember that the difference in the boiling point of hydrogen with the rest of the components was basically quite high. There is a large difference in the boiling point, and that is how we have been able to separate out this hydrogen from the mixture. And we have talked about the Linde-Brown process where we have used or take help of the liquid hydrogen in a condenser evaporator, where we have tried to separate them out. And now we will be talking today about it is a continuation to that process of generating hydrogen from the coke oven gas. Today we will be talking about another popular process called air liquid process for separating hydrogen from the coke oven gas. Now, this is another cryogenic process where we will be seeing how we could take help of this harness this difference in the boiling point, but this process will be different from the earlier one in terms of providing the refrigeration. So, in the Linde-Brown process, that was mainly meant for, as I told you earlier, that was meant for producing ammonia. So, we had a composition of hydrogen and nitrogen, and that finally someone if wants to separate out hydrogen from nitrogen, it is again they have quite difference in quite different normal boiling point, and that can again be separated out using a condenser evaporator. So, here we will try to first of all talk about that air liquid process, and before that just we will try to give you a overview of what we have learned earlier. This is a coke oven composition of taken from the Barron's book, and these are the typical normal boiling point, just to recapitulate. And you can see that the normal boiling point of nitrogen is quite different from the rest of the gas. The nearest possible one is the nitrogen, and all of them are quite higher than that and the most of the higher boiling the higher hydrocarbons like ethane, propylene and ethylene. So, those are also present in this if they are present in small quantity, that can also be separated out, and they are quite their boiling points are quite different from the boiling point of hydrogen. So, this can be utilized in again in this process. So, this is another coke oven gas composition which we have talked in the earlier class. And then we have learned about this Linde-Brown process, where we have said that we have a compressor where we have compressed this coke oven gas, and finally, that was cooled with the help of LN2 in this condenser evaporator. So, this condenser evaporator was giving us the finally, of course, we had to separate out this nitrogen and ammonia, and the CO mixture was there, and from there we have used a CO scrubber because it was having some amount of CO present in this, and finally, we got this nitrogen and hydrogen mixture. So, it was quite elaborate process. You might have noted that there are different heat exchangers and I mean starting from 2 stream exchanger cooled with the ammonia, we have 3 stream exchanger, also we have 2 4 stream exchangers, and apart from condenser and evaporator, that is again another kind of heat exchanger and phase CO scrubber. But the main idea is that we have a coolant which is coming from I mean it is not like ordinary thing that is available, but of course, we need some when it is needed in bulk quantity, we have to look for an air separation process. So, from the air separation process or cryogenic air separation process, we get this liquid nitrogen, and that liquid nitrogen will be supplying the necessary refrigeration in this process. That is what is the Linde-Braun process. But is there any possibility that this refrigeration can be provided within the process itself? And that is how this air liquid process has evolved. It was done by Claude, and later on we will learn, when we talk about the cryogenic liquefaction process, we will see it will be better understood at that time. So, at this moment you just go through this process, and again we will be coming back, or you will be able to understand this process better probably when you have learned about the cryogenic liquefaction cycles. So, here comes this coke oven gas. We start with the coke oven gas, and first of all we compress it to nearly about 25 atmospheric pressure. So, this is about 2.5 MPa, and from there we take it to directly into one 3 stream exchanger. We will try to identify the other streams which are cooling this high pressure coke oven gas. Then comes as I have told earlier also, this will come to if it is cooled to a sufficient level, it is coming to nearly about minus 65 degree centigrade. So, at that temperature you will find some propylene will be condensing. So, this propylene will be taken out from here, and the rest of the compressed coke oven gas will come, and that will come to another heat exchanger, that is again a 3 stream heat exchanger, and this will continue to pass through another phase separator, where mostly the ethylene, ethane and some portion of methane will also get condensed, but not everything will be getting condensed here. So, all these components like as I told you, the methane a part, and ethylene and ethane, they will be coming over here and they will come out. Okay. But what is about this compressed coke oven gas? This will continue to flow through this, and then we will put it in a again condenser evaporator. So, on this part we will be putting it as a compressed one, and it is coming over here. So, this is coming to this side, and this will produce basically it has to be cooled, right. But as we have understood that earlier, this cooling was provided with the help of liquid nitrogen, but we do not want to use liquid nitrogen. So, then we have to arrange for something which will provide the necessary refrigeration here. So, what we have here, imagine that we have produced some amount of methane here, liquid methane. So, this liquid methane, and along with other components, it will be not only liquid methane only. So, that will come out from here, and then again we will expand it, and it will put it back to this side. So, if we have been able to create some amount of liquid methane, we will see how it really has been produced. So, we will put it as a refrigerant on this side, on the one side of the tube, and once we have provided that refrigeration, So, what we will find is basically the hydrogen will be coming out in the form of gaseous hydrogen, and this gaseous hydrogen, it is under pressure, and this, because we have not expanded this hydrogen, right. So, this is coming from here and we have taken it into this tube side, and here on this side, this methane is getting methane along with say CO and other hydrocarbon would be there in this, and they will be coming over here, and it is expanded and it will be providing the refrigeration. So, on this side you have the gaseous hydrogen. So, this gaseous hydrogen which is under pressure. So, we will try to put it in an expander. This expansion process is different from this expansion process. This is the JT expansion. We will talk in details later on while talking about the liquefaction part, but this is what is called an isentropic expansion or isentropic expansion, and that means its entropy remains constant, whereas this is isenthalpic expansion where the enthalpy remains constant in this process. But there are certain advantage of this expanding the things with the isentropic expansion, particularly for gases like hydrogen. So, this gas will be expanded and it will generate nearly about, when it comes out, it will be nearly about minus 205 degrees centigrade. So, this gas will come out from here and it will be taken as the hydrogen product that will be mixed with certain amount of impurities, which can always be separated out using the PSA based system. Now, what is about this gas which is there on top of it? You have this mixture as let me change the color of it. So, this is where you have this gaseous vapor on this side, or you can say here this is this basically this part is the vapor part of this CO and CH4, and that is quite cold, and that will be taken out from here as a methane plus CO mixture. So, before it is in cold condition. So, that cold will be retrieved basically before it goes back to the since it is methane and CO mixture, it can always be used as fuel. So, but it is cold fuel. So, basically you can understand that we will take its cold to cool the incoming high pressure gas when it was coming to this condenser evaporator. This CH4CO part, that is which has been liquefied, basically this refrigeration has come from here. So, initially when the process is getting started, you do not have any liquid over here, but some portion of the gas at that pressure, this high pressure will be collected over here, and then it will be expanded, and then it will provide you the some amount of cooling, which will be cooling the high pressure incoming gas, and then in the steady state process you will find that it is providing you the methane plus CO mixture. So, that is how we are trying to separate out the methane and CO and hydrogen, and basically get this hydrogen in the form of gaseous hydrogen. This is still in the gaseous condition, and that is why it is collected on this top part, whereas this liquid part this methane CO which has become liquid, that is collected as liquid at the bottom part of this condenser evaporator. So, this part is getting condensed, and a part of it is again here, this is getting evaporated. That part was basically, this is at this point, this is pressurized one on this side when it has come, it is under low pressure. Because we have expanded, as I have told you here, this is a JT expander. So, this JT expansion is done and finally, it is coming as low pressure liquid. So, that is providing the refrigeration, but the main refrigeration is basically has been created by the help of this expansion engine. It is unlike that Linde-Braun process where liquid nitrogen was supplied from outside. Here this high pressure gas, because of this expansion in the isentropic isentropic expansion, it will produce the necessary refrigeration. So, this is how this air liquid process is meant for producing the hydrogen from the coke oven gas. Now, in both the air liquid process as well as in the Linde-Braun process, we have seen there is something called condenser evaporator. So, it is of course, a 2D figure which may be a bit difficult for you to realize. So, let us first of all let us look into this air liquid process as a whole. So, this is how it is. So, we have the coke oven gas, it is getting compressed and then it is cooled with the help of this 3 stream exchanger. Then we have separated out some portion of the propylene etc. and here again it is cooled into this 3 stream heat exchanger, and finally, before it comes to this condenser evaporator, all this ethylene, ethane and methane will be separated out from here, that will be taken out from this process. So, here a desktop it will as I told you that this is the high pressure, this coke oven gas, it is coming on the tube side, and here we have the gaseous hydrogen. This is still under pressure. So, before it goes it will be expanding and this will come to nearly about 205 degrees centigrade, and it is finally coming out as hydrogen in the form of gas, but before it goes out at room temperature or atmospheric temperature, it is first of all it is atmospheric pressure. This was at 25 if there is no pressure drop in the system. Then it is coming to atmospheric pressure, but this is at quite low temperature. So, this low temperature or this cooling will be basically that cooling will be taken by this high pressure incoming gas and before it goes out to the atmosphere. On the other hand, as I told that this methane and CO mixture will be expanded and that will be coming over on top of it on the condenser evaporator part, that will be collected over here and provide the refrigeration for this methane, which will be collected over here. So, this methane part, a part of it will also be I am sorry, this will be taken back, this evaporated part, and that will again be at low temperature. So, that has to go back before that we will take out its cooling. So, this is CH4 plus CO and that will come out of the system. So, this is how it looks like this liquid air process, air liquid process. Okay. So, what is common in both these two systems is this, as I told you that this condenser evaporator which has been drawn in 2D. So, let us have a look into this in detail. I will just show you a small video here that will tell you how this is, how it looks like. Of course, the piping etc. is not shown here, just the structure is given here. So, this is what is that tube bundle you can see, and this is the two vapor domes. Okay, I am showing it once more. This is how this condenser evaporator looks like. This is what is that tube bundle, and this is top cover, this is the bottom cover, and this is the cylindrical part, and this is another top cover of it. Okay. So, now let us look into this I am sorry fine. So, these are the 3D structure, as I told you that this is the tube bundle. So, on top of it we have one cover, this is this part, and on the bottom part of it is if we look at it or identify it with this is the bottom part, we have covered this on this side also. Now, this is that annular part where we have on this side we have provided the that liquid nitrogen was poured in from here in the Lindebrand process. We said that we are putting liquid nitrogen. So, this is filled in with the liquid. So, that means all these tubes were basically cooled by the liquid nitrogen. So, here in this space we were filling it up from this part, and this inner part which is basically coming, or all the gas, high pressure gas is coming over here, and they are coming in contact, passing through this tubes are getting collected over here. This gaseous part will be collected over here, collected over this part, and the liquid part the refrigerant part is on this side, on this outside this tube. So, they are not getting mixed with each other. On this side in the Lindebrand process, we said that we have this N2 plus H2 plus CO, and we were providing on top of it basically I am sorry, this was not, this was the top product from here. I am sorry, this is the top product which was coming from here, and then it went to the CO scrubber, and outside this we had liquid nitrogen. We have provided liquid nitrogen in the Lindebrand process. So, this was the one which has been collected from this dome, and this was taken to the LN2 scrubber. But for the what is called this air liquid process. So, this was basically the methane and CO. This methane and CO was here, this was at this, I am sorry. So, at this point it was coming as H2 plus CH4, and then we had the CO. These three things were coming. Out of that, this H2 was collected at the top, whereas this methane and CO was under pressure, and they were getting collected over here or getting liquefied, and this gas high pressure gas was expanded, as we have learned in the liquid air process, air liquid process. So, this was high pressure gas, we have expanded it and put it on this side. So, this will be collected over here. On this end this is providing, outside this tube we have this liquid methane plus CO, and inside we have the vapor where this CH4 plus CO will condense, it will collect, it will be collected over here. The hydrogen gaseous form it will be collected from the top. So, this is still at high pressure in the in case of air liquid process. So, this is how it looks like in both the Lindebrand process or in the air liquid process. Now, we have a question that if it could be either be it liquid hydrogen or say be it liquid nitrogen or I mean in the air liquid process we have used this we have used that expansion engine. So, why did we do such an elaborate scheme? Say if in the Lindebrand process also we had that coke oven gas and we could have put directly into it and cool it with the liquid nitrogen, or this coke oven gas we have compressed it, we could have directly put into this condenser evaporator and everything was getting condensed here except this hydrogen. So, why it was necessary to have such an elaborate scheme of putting so many heat exchangers and then I mean 2 stream exchanger, 3 stream exchanger, then 4 stream exchanger in case of Lindebrand process, and in case of course, air liquid process which is much simpler in nature, but still we have at least 2-3 stream heat exchanger apart from this condenser evaporator. So, was it really necessary to use all these components and then to have this kind of generation of this H2 in the process for generating H2 from this process. So, basically the answer to that question is yes, it is necessary, because it is not only the hydrogen, but we have another I mean all these components where we have seen that be it methane, be it the CO or other components like ethylene, ethane, though it was present in small quantity, but those are very I mean useful things. So, the ethylene for example we are making polyethylene. So, that kind of component, if it was not collected earlier, it would have come along with this mixture and finally, it would have gone as an waste. So, in order to retrieve all these components one by one, we have that elaborate process where you could understand that every useful quantity which is there in meaningful I mean amount. Basically, it should not be such that after separation this product is such that its price is more I mean less than the separation process. So, the separation process should not be costlier. So, if we are able to retrieve a meaningful amount from this process, we should try to separate them out. So, that is how we have seen that the ethylene, ethane, those components are to be separated from those process. Along with that we should try to get this hydrogen. So, this is about this I mean this is about this separation of hydrogen from the coke oven gas. This has been taught mostly from the cryogenic systems by Baron. So, here comes this conclusion that again this is a potential source of hydrogen. If we have the coke oven gas, coke anyway is necessary for the steel making process, and along with that this coke oven gas can be a potential source of gaseous hydrogen. And moreover, we have earlier talked about this Lindebrand process. Now, we have learned about the air liquid process. This air liquid process is basically based on an expansion engine, whereas the other one, that Lindebrand process, is based on the supply of liquid nitrogen. So, with this we come to the I mean an end on the hydrogen production part, and in the next class I mean hydrogen, we have talked about the hydrogen production part from the conventional fossil fuel or fossil resources. In the next class, we will try to look into the non-conventional or renewable energy resources, mostly that will be water splitting, that we will take up in the next class. So, thank you for your attention.